Welcome to 3.1, Factors and Multiples of Whole Numbers. So first we're going to go over some terms that we're going to have to know. So up first is factors. Factors are an integer that divides into a number and gives another integer. For example, 3 is a factor of 12 because 12 divided by 3 gives you 4. So 3 is a factor of 12. Multiples. A multiple is a product of a number and any integer. An example of a product is 24. 24 is a product of 12 because it is 12 times 2 gives you 24. Multiples are kind of like the opposite of a factor. Factors make up a number, whereas multiples are made from a number. Prime numbers. A prime number is a number that can only be factored by itself and 1. So 3 is a prime number because it has no factors other than 3 and 1. Nothing else divides into it. Another prime number is 19. The only numbers that you can divide 19 by are 19 and 1. Prime factor. A prime factor is a factor that is also a prime number. 3 is a prime factor of 12 because 3 is also a prime number, but 4 is not a prime factor of 12 because 4 can be also divisible by 2. Prime factorization. Prime factorization is breaking down a number into its prime factors. The prime factorization of 12 would be 3, 2, and 2 because 12 gets broken down into 3 and 4, but 4 is not a prime factor, which can be broken down into 2 times 2. So the prime factorization of 12 is 3 times 2 times 2. So something else we should look at are the first 10 prime numbers. These are numbers that we are going to want to memorize as they will help us with prime factorization. The first 10 prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. Our first example here is we're going to find the prime factorization of 3,300. To do that, we are going to use what's called a factor tree. A factor tree starts out with your main number, or the number you're trying to find, and breaks it down into its factors until they are all prime factors. So at the top of your tree is your starting number, which is 3,300. This, we can tell, breaks down, is divisible by 33 and 100. 33 times 100 gives us 3,300. Now we look at each branch separately. So first we look at 33. This can be divided by 3 and 11. Next we look at the other branch, the 100. We know that 4 times 25 gives us 100. So 4 and 25. Now we look at our next row. 3 is a prime factor, so we are done. 11 is a prime number, so we are done. 4 is not a prime number, so that can be broken down even further. 4 can be broken down into 2 times 2. 25 is not a prime number. It can be broken down into 5 times 5. So the prime factors of 3,300, the prime factors are a 2, a 3, a 5, and an 11. The prime factorization of this number is 2 times 2 times 3 times 5 times 5 times 11, or, which is equal to 2 to the power of 2 times 3 times 5 to the power of 2 times 11. Next, we will find the greatest common factor. The greatest common factor is the largest factor that can be found in all of the following numbers. In this case, 138, and 198. One way to find the greatest common factor is to find the factorization of both numbers first. To find the greatest common factor of these two numbers, 138 and 198, we must compare their prime factorization. 138 had 2 times 3 times 23. 198 had 2 times 3 times 3 times 11. The greatest common factor can be found by finding the similarities between the two prime factorizations. So they both have a 2 and they both have 1 3. So the greatest common factor is 2 times 3, which is equal to 6. GCF stands for greatest common factor is equal to 6. Here we are finding the least common multiple of 18, 20, and 30. The most consistent way to find the least common multiple is to use, again, the prime factorization. So we will find the prime factorization of 18, 20, and 30. So the prime factorization for 18 is 2 times 3 times 3, or 2 times 3 squared. The prime factorization for 20 is 5 times 2 times 2, or 5 times 2 squared. The prime factorization for 30 is 5 times 3 times 2. To find the least common multiple of 18, 20, and 30, we look at each prime factorization and take the greatest power of every number's occurrence. So for example, we see there is a 2 in 18, but we see there is a 2 squared in the 20, and just 1 2 in the 30. So our least common multiple has to contain a 2 squared. Similarly, there is a 3 squared in the 18 and a 3 in the 30, so the highest power is the 3 squared. So there needs to be a 3 squared in our least common multiple. And finally, there is a 5 in the 20 and a 5 in the 30, and the highest power is 1, so the least common multiple has to have a 5 as well. Now, every prime factorization of every number can be put into this final factorization, and so the least common multiple, or LCM, is equal to 2 squared times 3 squared times 5, which is equal to 180. Next, we will be solving problems using the least common multiple and the greatest common factor. First, we will try to find the side length of the smallest square that can be tiled by 40 by 16 centimeter rectangles. So in this question, we have rectangular tiles that are 40 centimeters by 16 centimeters. We want to know what the smallest square will be that we can make using these 40 by 16 rectangles. So in other words, we want to find a number for the side length of this square that both 16 and 40 will both go into. So that is the least common multiple. So to do that, we need to find the factorization of 16, which is 2 times 2 times 2 times 2, or 2 to the power of 4, and the factorization of 40, which is 2 times 2 times 2 times 5, or 2 to the power of 3 times 5. So our least common multiple has to have a 2, and the highest power in the two factorizations is a 4. Our least common multiple also needs a 5, and our highest power is a 1. So our least common multiple is 2 to the power 4 times 5, which is equal to 80. So the smallest square that can be tiled by 40 by 16 centimeter rectangles has a side length of 80 centimeters. Now we're going to look at what the side length of the biggest square that can tile a 40 by 16 centimeter rectangle is. So be careful of the wording between these two questions. In this first question, it was asking what is the smallest square that can be tiled by the rectangles. So the smallest square is looking for the least common multiple. In our next question, it is asking for the side length of the biggest square that can tile a 40 by 16 centimeter rectangle. So it is asking for the biggest squares that will fit perfectly into a 40 by 16 centimeter rectangle. We are looking for the biggest square that fits into that rectangle, so we are looking for the greatest common factor. What this question wants is if we have a 40 by 16 centimeter rectangle, what is the biggest square that will perfectly tile this rectangle? So we want to find the side length of this square that fits into both 40 and 16. So to do that, we find the greatest common factor. Since we want the greatest common factor, we will look at the prime factorization of 16, which was 2 times 2 times 2 times 2, and the prime factorization of 40, which was 2 times 2 times 2 times 5. Now we make pairs with the 2 prime factorization. We see there is 1, 2, 2 2's in both 16's prime factorization and 40's prime factorization. So our greatest common factor will also have 3 2's, which is equal to 2 to the power of 3. So our greatest common factor is equal to 2 to the power of 3, which is equal to 8. So the side length of the biggest square that can tile a 40 by 16 centimeter rectangle is 8 centimeters. Thank you for watching 3.1 Factors and Multiples of Whole Numbers.